So, good morning.
We are still with introductions to multivariate statistical modeling. In the first two half-an-hour lectures, I have given you some introductory aspects from variables, from variate, from models, modeling, then principles of model building, related stuffs. Today we continue with introduction, but today our discussions is on statistics to model building. I'll show you practical problem and hypothetical problem for a small company, and then I'll show you how can we convert this practical problem to a statistical problem, and thereafter I'll show you different kind of multivariate modeling from the dependence models to interdependent model. And I'm sure the earlier lectures have given you some idea of the subjects of these subjects from its applications point of view. And today you will see that some more on the techniques point of view, and in the next class you will see some more of the techniques point of view.
Last class, what we have discussed that your data equal to pattern plus error, pattern plus error. So, how do we extract pattern? That was the issue. So, with respect to this, we will discuss now what are the statistical approaches or statistical approaches to problem solving. Statistical approaches to problem solving. If you see the slide, you see that here we will start with practical problem, then this practical problem will be converted to statistical problem, and statistical problem will help us to generate statistical solution, and this statistical solution. So, if I say that first one is practical problem, second is statistical problem, third one is statistical solution, then this statistical solution must be practical enough. So, that is practical solution. Now, whatever solution you get, statistical solution is converted to practical solution, and it should be checked whether the practical problem is truly solved or not. That is why this cycle, and if you see the slide, you see that it is a basically cyclic one, your practical problem, and that is the crux of the matter. If you find out the practical problem nicely, identify and define the problem nicely, because rest of the things are following it. So, then the statistical problem, then your statistical solution, and finally, the practical solution. So, many a times we falter in effectively defining the practical problem. Getting me? So, what is practical problem? How do we understand a practical problem? So, I have started with a small example in last class, that a small company in a city doing business primarily local at the local level, and the company is monitoring its profit and sales volume, and it is observed that absenteeism is quite high, and there are machine breakdowns also, and in order to improve that business performance, marketing department is also established maybe recently, and then they want to check that how the marketing department is performing. Now, here what is your practical problem? If I go back to this slide again, what is the practical problem? The practical problem is, as I told you, that there is threat to profit and sales volume, high absenteeism and occasional to frequent breakdowns, and maybe the poor performance of the marketing department may not be, but I am assuming that the performance of machining department is also not good. That means, the threat to how to overcome threat to profit and sales volume. If high absenteeism is causing lower profit, and that what is the extent of that effect, then it is better for the management to take actions. Now, we will convert it into a statistical problem. If you really want to build a statistical problem from a practical problem, these are the few items or steps which you must follow. First one is identify variables of interest. In this example, profit, sales volume, percentage absenteeism, machine breakdown in hours and M ratio. These are the variables what we have identified. Now, identify response variables. Out of those variables, all the variables, what are the response variables? Now, here by response variable, what I mean to say? By response variable, we want to mean to say that these variables are affected by presence of other variables in the system. Getting me? In other words, what we can say? Dependent variable. So, y1 and y2 are response variable, they are dependent variable. Why? Because the absenteeism, machine breakdowns and M ratio can influence profit and sales volume. So, immediately the next objective is identify the explanatory variables and find out the dependence relationship. Getting me? For this particular problem, although it is little bit difficult at this moment, that why suddenly we are going for this dependence modeling, what are the different types of dependence modeling techniques are there, but you should not be what I mean to say, you should not be governed by the techniques. That is the one of the threats. Many times what happen, you know many multivariate techniques and you think that your problem will fit to that technique. Please do not do this. So, that is why here I have written in the finding the relationship y is function of x. We have not said that it is a linear relationship or nonlinear relationship, or it is a regression, or it is something some other way of doing things, it is nothing mentioned. So, you must be driven by the problem at hand. So, our problem at hand is threat to profit and threat to your sales volume, and so we got the response variables where we want to concentrate, and accordingly some the other explanatory variables mean which there are the variables which explain why there is variability in profit and variability in sales volume, and then function of y is fx. In statistics, statistical modeling, the variability is the crux of the matter, please understand. you must understand the variability structure. In case of one variable there is variance, in case of several variable there is variance and covariance, and in totality we say that is the covariance structure. So, that covariance structure this will give you the pattern. The pattern you want to extract, this will be given by the covariance structure. Okay. So, let us see the statistical problem here. The statistical problem is that variability in profit and sales volume. By variability we are saying that definitely there is high variability caused by x1 which is percentage absenteeism, x2 machine breakdown in hours and x3 M ratio. There may be linear relationships. So, now you are coming to statistics domain, so you have to assume something. There may be linear relationships. Any problem up to this? Do you have any query? Any query from your side? It's okay. This side, no problem. Yes. Then I want to show that we say that fine, there is your relationship, statistical way you can examine the relationship, and we also assume that the relationship is linear. Now, let us see then pictorially. If you see this particular figure here. What we have said that y1 is affected by x1, x2 and x3. What is y1? y1 we have said y1 is profit, correct. So, y1 is profit, x1 is percentage absenteeism, x2 is breakdown and x3 is machine hours. Okay. So, y1 is profit, x1, x2, x3 absenteeism and your breakdown hours and M ratio. Now, this is the linear relationship between y1 and x1, x2 and x3. You may be wondering that what is x0 then? Okay. That x0 is a constant value which will be later on in multiple regression you will be knowing that x0 will be giving a value of 1. For all observation that one value will be given, and beta 10 will be the intercept, means irrespective of the effect of all those explanatory variable considered here, but there will be still some value for y and that will be determined by beta 10. Getting me? But it you slowly you wait, later on we will see. But the sole purpose of this particular figure is that what I mean to say that y1, if you want a linear relationship you can pictorially represent like this. Similarly, for sales volume also you can represent like this. In the pictorial representation, please keep in mind two things. First of all, the arrowhead is, see that it is suppose x1 versus y1, if you consider that the arrow basically starts from x1 and ends with y1 and arrowhead is at the y1 level. So, that it simply indicates that y1 is a dependent or affected variable and x1 is the causal variable or explanatory variable. And another issue is this epsilon 1. Epsilon 1, that is basically some error component, as I told you that data has two parts, one is pattern and error. That apart from this error, the rest of the things are basically pattern, beta 10, beta 11, beta 12, beta 13, that will ultimately reflect the pattern. So, similarly for y2, but for this particular company, your Y1 and Y2, their sales and volume and your profit for the same month, that is simultaneously occurring. So, if you go by two different models, linear models, will it suffice? That is why what I have written, that Y1, Y2 are measured simultaneously, they are covariing also.
Sir, one question.
Please.
You said that there may be a linear combination of those variables. This is linear model. Now here epsilon 1 and epsilon 2 are noise terms. Let's say y1 can be linearly
Related.
dependent on x1, x2, x3.
Yes, yes.
Now there may be a bias term other than the noise.
That is x0, beta 0 is that.
Like beta 1p xp plus epsilon 1. So, what is this?
This is the bias term.
Now, what I am saying now further, that y1, y2 you are measuring simultaneously. Do you want to keep the structure intact while estimating, while modeling? What is the structure here? Both things you are measuring simultaneously. So, you see the next slide here, the next slide left one. So, what you are doing here, you are basically saying no, both are occurring simultaneously and they are multivariate observations only. So, what I want to keep them in one model. I will not go for two linear models, only in one linear model I will do this. Okay. But there is another problem. What is the other problem? Other problem is y1 is basically and y2, there may be relationship between the two. It may so happen that y1 may affect y2. So, that means that y1 is not only a dependent variable or response variable, it also becomes a causal variable or explanatory variable. It all depends on the situation. Suppose in your situation this is not the case, no problem, but many a times what will happen, you will find out that this type of structure is there. So, when such a structure is present in the practical problem, how can you ignore it? You cannot ignore it. That means, you have to keep the practical, that behavior, real behavior intact, and then find out the model, not the other way around. Find out a model, feed the data, and accordingly you say that is the behavior of the system studied. It is not like this. Okay. So, actually what happened, there are few models, by saying these few models are I can say discussed pictorially. One is multiple regression, then multivariate regression, then path model. Later on we will see that what are all those things. Now, what is what purpose effectively, basically from statistical sense? I said that what are the purposes of multivariate modeling at the beginning, but from statistical sense, what are the purposes? You see, what first purpose is description. Any model you build, it definitely describe what is the problem at hand and what are the purpose of that study and what are the different variables involved in this particular problem and what are the, how these variables are measured, how these variables I can say are stored or kept, what from what data source it is found out, whether it is a primary data, I mean you have gone and collected or you have taken from some other source. So, all those things are coming under description. Then this description part should be done ritually. In fact, everything should be done ritually. Descriptive part you should not falter, because this is the problem definition part. Then explanation. What is explanation? The relationships between the variables, amongst the variables. What is the relationship? That is coming under explanation. Then prediction. Okay. So, whenever we talk about any model, we talk about description of the problem, we talk about explanation of the relationships of the variables, building which is basically used to build the model, and prediction. Now, many models are not able to predict. So, that means in a model, if in any model, if the first two portion is missing, then that is not a model. You will just develop a structure like this, a schematic diagram like this, and describe something, and you will say it is my model. That is a description part only. That is not the model. You have to explain the relationship. That means here in this particular diagram, this is the description plus relation. Where is the relation? Relation is gamma 1, gamma 2, gamma 1 3, gamma 2 1, gamma 2 2, these are the relations. And without this gamma and beta values, this is only a description. If you use certain model which will give you all those beta gamma estimates, and then explanation is completed. Now, using this side, the left hand side plus the estimates of beta gamma and errors, if you predict some values for y 1 or for y 2, that is what is prediction. Any model.
Sir, here you have assigned some weights with say gamma 1, gamma 2.
This I understand the biology. This is the first class, the second, basically second lecture here. Now, this what I am trying to give you a pictorial view only here. The how this beta 1 gamma 1 or beta gamma 1 1 beta 1, all those things, I mean what is the issue and how it will be estimated, all those things will come slowly. In the subsequent lectures you will be knowing the estimation portion.
My question is in earlier diagram there is the dependency between x1 and x2, but there no weights are assigned.
Where? This is the only diagram. This is the only diagram.
Between x1 and x2 there is no weight, or between x1 and x3 there is no weight, or between x2 and x3 there is no weight.
Okay, okay, fine. I understand now. Your question is this one, this side. Actually, in this case, this is a representation of multivariate regression. Here we consider all these variables are purely independent, and in this model case, this is a pictorial representation of path model. Here we consider that the independent variable can vary, can co-vary. Getting me? But in reality, you will not find out that all variables are independent, truly independent. So, this is a better representation. Okay. Slowly, just if multicollinearity is a problem, then this is the case. Later on, after in few subsequent lectures, it is there. Okay. Now, what are the different multivariate models that will be discussed in this subject? Okay, so I have given you some idea of that what is multivariate analysis, what is multivariate statistical modeling, what do you mean by multivariate, and also different data types, and how practical problem can be converted to statistical problem, and in statistical domain what are the problems, and then there we will now we will see that that there are different types of multivariate models, and primarily these models will be discussed in this subject. Okay. So, multivariate models are categorized into two broad groups. One is dependence model, another one is interdependence model. By dependence model, we say that there are two sets of variables. One is response site or response variables, another is explanatory variables. Getting me? So, there are two sides. Explanatory variables are used to explain the response variables. So, that is what is dependence. That is the dependence structure. Okay. And interdependence, if you see, that interdependence model, there is no response site. All variables are coming under one bracket. All variables under one bracket. What we mean to say? There is relationship definitely, but within the same set of variables. There is no categorization of that one set is dependent and variable or response variable, other set is explanatory variables. So, based on this concept, so there are dependence model, there are interdependence model. So, in dependence model, MANOVA is there, which is multivariate analysis of variance. Multivariate analysis of variance. Multivariate analysis of variance. I think all of you know that what is analysis of variance, that is ANOVA, and it is presumed that the ANOVA is known, then only MANOVA can be understood. Then multiple linear regression, then multivariate linear regression, then your path model, structural equation modeling is another component. In addition, logistic regression, discriminant analysis. There are many more dependence model, but in this sets of models, what is the basic picture is that we have two sets of variables, one can be affected by other set of variables, and we can build model like y equal to function of x. This type of relationship model we can build. Other sets, group, that is what I say, the interdependence model. So, under interdependence model case, there are principal component analysis, factor analysis, cluster analysis. Here we will not segregate the variables into dependent or independent side. We take everything as x, one set of variables, and then we want to see the covariant structure of these x variables. There are many x variables, and based on this structure, our primary objective in principal component analysis is reduction of dimensions. So, dimension reduction. Factor analysis, not only dimension reduction plus naming the factors. So, dimensional reduction plus naming the factor. In cluster analysis, we want to group the individuals, not the variables. Factor analysis and PCA, we basically group the variables. So, then we reduce the dimension, and in cluster analysis, we will not group the variable, we will group the individuals or items or objects on which data is collected, and then we make several clusters. okay, cluster 1, cluster 2, cluster 3. So, like this several clusters will be formed.